Hello everyone, this is Javi, a PhD from Columbia University. On behalf of the team, it's a great honor for me to present our paper MoDE, Clip Data Experts via Clustering. Mixture of experts is a popular machine learning technique where multiple expert networks are learned to develop strong representation for each input sample. However, previous approach apply MoE within a single deep neural network and essentially determine expert routing based on the subregion. In this project, we introduced the concept of data expert, which uses the data distribution to explain the model capability and split the dataset to learn several data experts as well as their example. Below, I will use contrastive language image retraining as one example to explain what MoDE is. So CLIP aims to align the image and the language with similar semantics. Given a set of pairs as one example, the CLIP aims to connect the image with its paired caption and separate the images from the unpaired ones, and vice versa. Generally speaking, a single image may be worth thousands of words. It can indeed be described by captions of different topics. Like the one shown here, we can see both a kite climbing a tree and also a tree god stopping the cat. And by comparing different images, we can also find captions of similar topic, but with different details. However, for the data crawled from the internet, for each image, the caption is reasonable, but none of them is complete. And we can even encounter general description which does not talk about any details about the visual content. Then we do see two data pairs that share the same image, but with captions corresponding dramatically different aspects. So if we still follow the old clip training pipeline, we will see false negatives. Take the first image as one example. By definition, it should be separated from the second caption. However, it is the same as the second image and should essentially be aligned with that caption. And such false negative will hurt the training effectiveness and should be reduced. One way to work around is to separate the data. Say a model is only trained to describe the animals like cats and tigers. Another one is only for non-living objects. If we don't mix all of them to train the same model, the false negative can be removed intuitively. Meanwhile, by comparing the unpaired captions, which has similar semantic topics but of different details, the model can learn to extract more discriminative features and further improve the training effectiveness. Such samples are also called hard negatives. This, the false negative, is caused by the fact that each caption cannot fully describe the visual detail. We propose to separate along captions and perform k-means clustering on the same-sex language embedding of captions and split those conflicting pairs to different clusters. Then, for each cluster, we just train a single model and explicitly align the image with a single caption. The model should also perform well on all of the tasks that require the knowledge exhibited in the corresponding training data, and thus called a data expert. For the application of MoDE on large-scale training data, we also need to balance the effectiveness and efficiency. First, we want to explicitly indicate what the data expertise is, but should also maintain the system size reasonable. As such, we consider cluster hierarchy and use a set of fine-grained clusters to describe what each data expert can do. Then, at the test time, for each task, we just extract the language embeddings of its description as the required knowledge. By comparing the task description against the expertise of each data expert model, we can decide the routing of models, which is purely based on the statistics, and the routing is thus called data-driven. In practice, we compare task description with fine-grained clusters and determine the weight by accumulating along the cluster hierarchy. Compared with the large clip model trained by other companies, the mixture of data experts improves both accuracy and efficiency. So the x-axis indicates the training cost, and the y-axis is the accuracy. The diameter of circle indicates the model size, and we use a set of small models to beat a giant one. Further, we reduce the minimum requirement of GPUs from 256 to 64. Besides the weighting of model outputs based on the language description, we can also directly concatenate the embeddings for downstream application. Here, we use higher accuracy in linear probing to indicate the better embedding quality by MoDE. As a summary, in this paper, motivated by the fact that the deep neural network is data-driven, we propose the concept of data expert and use data distribution to explain the expertise of model and propose the framework mixture of data experts. Then we apply MoDE in CLIP models and scale up the CLIP system capability efficiently. The learned models can also be applied in different task types. In the future, we are also planning to apply this work on other tasks, including generation. We hope our work can help with future application and have already released our code. Please feel free to drop us email if you have any questions.